Hello there, Mr. Sutton here with the AB Calculus 6-8 homework solutions on motion-free response. On this problem, I have two particles going along the x-axis, and between times 0 and 6, the position of particles p and r are given by these p and r functions here. Now we want to find all the times on the interval 0 to 6 where particle r is moving to the right. So if I want to know which direction r is going, I need to take this r of t function and find its derivative, its velocity. So r prime of t we can write as 3t squared minus 12t plus 9. I'm going to set this equal to 0 now and find some critical values so we can figure out where this particle is turning around. I can start by factoring a 3 out of all these. That's going to be 3 parentheses t squared minus 4t plus 3. And now I can factor a little bit further, two things that multiply to 3 and add up to negative 4. We've got t minus 1 and t minus 3. And now that means that t must equal 1 and 3. Now significantly, both of these are on the interval from 0 to 6. So that's potentially two places this particle's turning around that we care about. All right, let's do a little sign analysis. So we have 0, and this is r prime we're analyzing here. We have the critical values 1 and 3. And the other endpoint of 6. So I'll test out something on each of these intervals. 1/2 is a good thing to test out between 0 and 1. Plugging that in my r prime here, that's going to be a negative times a negative, which is a positive. Next, I'll test out 2 on that second interval. That's going to be a positive times a negative, which comes out negative. And I'll test out 4 for this last interval. That comes out positive, positive, so positive overall. So I notice here that r prime is positive on the intervals from 0 to 1 and 3 to 6 only. That means that my particle is going to be moving right on those intervals. Since this is on the x-axis, a positive velocity means we're moving in the positive direction, which is to the right. On this problem, we want to figure out all the times between 0 and 6 when our two particles are moving in opposite directions. So we already have some good intel on when r is moving to the left or the right from part A. We're going to do some similar sign analysis for p, or p prime rather, in order to figure out the direction that p is going. So taking my first derivative of p prime, that's going to be, let's see here, negative 2 sine pi over 4 t times a tail of pi over 4. So that's negative pi over 2. Sine of pi over 4 times t. And I'm going to set that equal to 0 now and solve. So my first step, let me just get rid of this negative pi over 2. If I divide both sides by that, I have sine of pi over 4t equals 0. And now I'm going to take the inverse sine of both sides. So let's see here. Where does sine take on a value of 0 on the unit circle? Well, that happens at 0, pi, because at 180 degrees you still have a y value of 0, 2 pi, and so on and so forth, basically every integral value or multiple of pi. But now I'm not quite done. I need to solve for t, not pi over 4t. So to get t by itself, I'm going to multiply by 4 over pi. That gives me 0. And then 4 pi over pi is 4. And now 8 pi over pi is 8. And we could keep going here. But we really only need values between 0 and 6. So we'll just stop there. Doing my number line now. I've got p prime. This is a p prime line. We start with an endpoint of 0. We have this critical value we just found here of 4. And then 6 is the other endpoint. Let me test some values between 0 and 4 and 6 now to see if I'm getting positives or negatives. Between 0 and 4, I'm going to test the value 1. So this is really, let's see here, pi over 4 for my angle. Sine of that is positive, but I'm multiplying by a negative out here, so that becomes negative overall. Next, I'll test 5 between 4 and 6. 5 pi over 4, that's essentially 225 degrees. That's below the x-axis. So the sine, the y value down there, is going to be negative. But I've got this other negative out front, so a negative times a negative gives me a positive. All right, so let's also juxtapose this with our r prime number line. Again, we created this in part A. I'm just kind of bringing it back here. And now let's compare to see where we have opposite signs. So let's see here. We start out negative for p prime and positive for r prime. So from 0 until, at the very least, 1, they have opposite signs. So they have opposite signs from 0 to 1. And then at 1, well, r prime changes to negative, and that agrees with p prime. So they're in agreement until I get to 3, at which point r prime changes back to positive. So from 3 to 4, which is where p prime changes to positive, from 3 to 4, we also have some disagreement. But then once p prime gets to 4, it is also positive, and these two positives are agreeing the rest of the way. So p prime and r prime have opposite signs on these two intervals. That means the particles, p and r, are traveling in opposite directions during these intervals. On this problem, we want the acceleration of particle p at time 3, and then we want to know if it's speeding up, slowing down, or neither at that time. So let's start by finding our acceleration. Our acceleration is going to be p double prime. Now, we know that p prime is this expression from part B. We found that in part B. P double prime, that's going to represent our acceleration. That's going to be, let's see here, this would be a cosine of pi over 4t times a tail of pi over 4. So this is going to end up actually being negative pi squared over 8 cosine of pi over 4t. So that's kind of a big mess. We want to find now if it's speeding up or slowing down at time 3. So we're going to have to plug 3 in to the acceleration and also the velocity, and then compare the signs of those things to see if they match or disagree. So let's do the acceleration first. They actually wanted the acceleration at time 3, so we need to do this. So let's see, plugging 3 into this mess. This is negative pi squared over 8 times the cosine of 3 pi over 4. Now, maybe you don't remember your unit circle. It happens to find the acceleration, you just need a constant, and this whole thing is actually one big constant. So you could stop here and have satisfied this part of the problem. But in order to figure out if you're speeding up or slowing down, you need to at least know whether this thing comes out positive or negative. This is cosine of a quadrant 2 angle, so that's going to be negative normally. But with the negative out in front here, this actually comes out positive. So at the very least, you can say this is greater than 0. Now, if you remember that this is really 135 degrees, and cosine of that is negative root 2 over 2, well, I mean, good for you. You could actually multiply this out and get the exact value. This comes out to positive pi squared radical 2 over 16. But again, all you really needed to say on here is that this came out positive. All right, so let's find p prime of 3 now. Let's go back and do that. They didn't say we had to do it, but we do have to do it if we want to answer this question. So that's going to be negative pi over 2 sine of 3 pi over 4. And again, this is 135 degrees. Sine of that is going to be, let's see, root 2 over 2, positive root 2 over 2, because we're above the x-axis there. So this then comes out to negative pi radical 2 over 4. Again, though, the most significant part of this is that this is a negative number. So we notice here that p prime of 3 and p double prime of 3 have opposite signs. What that means is that your velocity and acceleration are working against each other, and your particle p is slowing down at time 3. For this last part of the problem, they want us to write but not evaluate an expression for the average distance between the two particles over the interval 1 to 3. So first, before we can find the average distance, we just need an expression for the distance in general. So to get the distance, I need to use these two position functions, p and r, and I need to subtract them to figure out how far apart the particles are. But I don't really know for sure which way subtracting is going to give me a positive number. I always want a positive number if I'm talking distance. So I'm going to define a function. I'm going to call it d of t, and I'm going to define that to be the absolute value of p of t minus r of t. And the beauty of this is it doesn't really matter which one of these is a greater value. When I subtract them, I will end up getting their positive difference, their positive distance. All right, so now that I've defined this d function, I need to take its average. So for that, I'm going to do 1 over the interval length, which is 1 over 3 minus 1, times the integral from 1 to 3 of my distance function, d of t dt. And you could have actually just plugged this whole absolute value expression in there as well, but I just wanted to make it really clear, where this thing was, what the significance of this thing is. So there we go. They said we didn't have to evaluate it. We're done with this one. For this problem, we have Ben riding a unicycle back and forth. Ben is a man of many talents, I guess, along a straight east-west track. Here's our twice differentiable function b, modeling Ben's position on the track. And let's see here. The table above gives us some values of b and Ben's velocity v, which I guess you could also call b prime of t. And then we want to use the data for part A. We want to use the data in this table to approximate Ben's acceleration at time 5 with units of measure. All right, so to get the acceleration approximated, we need to find the average rate of change of velocity. Acceleration is the rate of change of velocity, so if we find the average rate of change of velocity on an interval that has time 5 in it, we'll be approximating Ben's acceleration. The best interval to use is 0 to 10. I mean, we could use 0 to any of these and still get credit, but why not pick the smallest interval? So I'm going to write that a of 5 is approximately equal to a rock from 0 to 10. So that's v of 10 minus v of 0 over 10 minus 0. And then let's see, v of 10, that's really 2.3 minus, this is 2.0. And you could stick units on the end of this and call it a day. The units is going to be meters per second squared. Whenever you essentially take the derivative of something, you're dividing by the input unit, the time unit in this case. But we could go a little further if we wanted to. This is a no calculator question. So this is going to be, let's see, 0.3 over 10, which we could turn into, let's see, move the decimal left one, so that's 0.03. And then that's going to be in, we said, meters per second squared. For this problem, they want us to interpret the meaning of integral from 0 to 60 of absolute value of v of t dt in the context of the problem, and then approximate it with a Riemann sum, but we'll get there in a minute. Let's do this interpretation part first. Whenever you're taking the integral of absolute value of velocity, you're finding the total distance. So we're talking about the total distance that Ben travels in meters. You got to have the units in there. They said using correct units. And they also want the time element here. If you leave that out, you don't get the credit. So this is from 0 to 60 seconds. All right, now that we've established that, to get the other point, we have to approximate using a left Riemann sum. So I'll say that this stuff is approximately equal to the following. So I've got a base of 0 to 10 for the first rectangle, and I'm multiplying that by the left height every time. So in this case, that's 2.0. Next, I have a base from 10 to 40 of 30 times the left height of 2.3. And then finally, base of 60, or 20 rather, from 40 to 60 is 20, times a height of 2.5. You could stick units on the end, which is, again, meters, and be done with this. Or if you really wanted to add all this stuff up, this is 20. This is, let's see, 3 times 2.3 would be 6.9, so another 0 gives us 69. And then 20 times 2.5, that's going to be 50. Adding all that up, we've got 89 plus 50 is 139 meters. For this part of the problem, they want to know for 40 to 60, must there be a time t when Ben's velocity is 2 meters per second? With justification. So whenever we're talking about something's derivative being guaranteed to be a certain value, we're generally invoking the mean value theorem for this. So let's take a look. We've got, first off, we have to establish that we have differentiability for this to even work. And we need differentiability for b of t, because that's the thing we're going to be finding the average rate of change of to figure out what the velocity has to be. So they told us that we have a twice differentiable function b. So since b is differentiable, the MVT will apply here. Let's go ahead and find the a rock over the interval from 40 to 60 of b of t. So that's going to be b of 60 minus b of 40 over 60 minus 40. And that ends up being 49 minus 9 over 60 minus 40. So this is 40 over 20, which does come out to 2. So we notice that we have an average rate of change of b of t that's 2 meters per second on this interval. Therefore, it follows that the velocity, which is the same as b prime of t, has to be 2 meters per second somewhere on 40 to 60 because of our mean value theorem. For this problem, a light is directly over the western end of the track. And let's see here. Ben is riding so that at time t, his distance between him and the light satisfies this equation here. It's essentially a Pythagorean theorem. So we want to know at what rate is the distance between Ben and the light changing at time 4. All right. So since we've got Ben with his own speed and we're asking about the rate at which his distance from this light is changing, multiple rates of change, this is a related rates problem. So we're going to start by differentiating this whole thing implicitly with respect to time. So on the left side here, basically taking the derivative of L squared, that's going to be 2L times dL over dt. Again, you have to implicitly differentiate with respect to time, so the dt is always going to be there. Next, on the right side, 12 squared gets differentiated away. It's just 0. It's a constant. But here, b squared, that's becoming 2b times dB over dt. And if we want to know the rate at which the distance between Ben and the light is changing, we're looking for dL over dt. That means we need to figure out values to plug in for L, B, and dB over dt. Well, let's start with the easy ones. Everything with a b in it is represented in this table up here. Now, they told us that time equals 40. That's the time this problem is being asked. So b of 40, we can actually look that up in the table. That's 9. And then dB over dt, that's b prime, or v of t, of 40, which is going to be 2.5. Next, to figure out L, we can use this equation up here. L is going to be the square root of 12 squared plus whatever this is at time 40. And we just said that that's 9, so 9 squared. So this is 144 plus 81. That's 225. Square root is 15. Or you could just remember this is a 3, 4, 5 right triangle in disguise. So plugging all that back in now, we've got 2 times 15 times dL over dt equals 2 times 9 times 2.5. And let's simplify this a little bit now. On the left side, this is going to be 30 dL over dt. On the right side, let's see here, 2 times 2.5 is 5, times 9 is 45. So just be a little creative what order you multiply these things in. And then dividing both sides by 30, 45 over 30, that's divisible on the top and the bottom by 15, so I can write that as 3 over 2. Now, what's my units going to be? Well, any kind of speed units in this problem is meters per second. So this is 3/2 meters per second. For this calculator-based free response problem, we have a particle moving along the x-axis so that its velocity is given by this weird-looking linear, trigonometric, quadratic sort of hybrid function. And they're telling us that at time 0, the particle is at position x equals 1. So they want us to, for the first part, find the acceleration of the particle at time 2, and then determine if the speed is increasing or decreasing at time 2, and then why or why not. So let's answer this one piece at a time. For the acceleration piece, we need to figure out, since we already have velocity and acceleration is the derivative of velocity, we need to find the acceleration, the v prime, at time 2. So I'm going to say that acceleration at 2 equals v prime of 2. And now let me actually do this on the calculator. So here's my Desmos. Let me put my v function in there. So we've got negative parentheses t plus 1 times the sine of parentheses fraction t squared over 2. And let's just close that parentheses. And we'll worry about the graph later. So all we needed to do here is do v prime of 2. Since we already have v defined, we're allowed to just take the derivative at a single spot without actually writing what the derivative of that looks like algebraically. So I'll just write v prime of 2 and take whatever number it gives me. That's going to be 1.588. So that's our acceleration. Now they wanted to know the speed, or whether the speed of the particle was increasing or decreasing at time 2 as well. So for that, we need to actually compare the signs of the acceleration, which we just found, and that's a positive number, with the sign of the velocity. So to get the sign of the velocity, we're just going to take the v function that we already have entered into Desmos, and instead of doing v prime of 2, let's just do v of 2.
and that comes out to negative 2.728. Now the key on this is that that's a negative number. Since a of 2 and v of 2 have opposite signs, that's telling us, since the velocity and acceleration are working against each other, that's telling us that our particle is slowing down, decreasing speed at time 2. For part B of this problem, they want to know all times in the open interval from 0 to 3 when the particle changes direction with justification. So if we're looking for a direction change, we're asking when is this velocity changing sign? So it would be helpful to know when the velocity equals 0, which we can figure out by graphing the velocity on Desmos. So let's go to Desmos. Here was v of t all graphed out, and I don't need this v of 2 stuff anymore. Now this is a little bit crazy, so let me change my window. I really just need to know what's going on between 0 and 3. So let me do negative 0.5, just a little bit beyond the boundary that I need, and 3.5, and see what we're looking at here. Let me just click on the function. So these little gray dots are telling me where my function is crossing the x-axis. We see it's happening at 0, 0, but we don't care about that because it's the open interval from 0 to 3, which does not include the endpoint 0 itself. We also have this other spot here at 2.507. So I'm going to write that down. T equals 2.507, and that's the only place between 0 and 3 where we're even changing sign here. So on 0 to 3, the sign of v changes only at time 2.503. Therefore, the particle changes direction only at that time. For part C of this problem, they want the total distance traveled by this particle from time 0 to 3. So for this, all we need to do is take the integral of the absolute value of velocity to make all the distances positive between 0 and 3. So absolute value v of t between 0 and 3. Do this just right on the calculator. So let me go down to a new level here, and what am I plugging in? Yes, integral, int, 0 to 3, absolute value, v of t, and then close the absolute value, and then d of t, and that comes out to apparently 4.334. So that's our total distance traveled. For part D of this problem, final boss battle, they're saying during the time interval 0 to 3, what is the greatest distance between the particle and the origin? Show the work that leads to the answer. So if we have a function x of t representing where our particle is with respect to the origin on the x-axis, we want either the highest or the lowest value of that x of t function. We're basically looking for the absolute min and max position of the original position function, and then we'll just take the higher, whichever of those has a higher absolute value, because we don't really care if the negative or the positive is further away. We just want to note which one is further away. Okay, so let's start by realizing that if I'm looking for maxes and mins, I'm really going to find those in two places. Absolute extrema happen only at the endpoints, which are 0 and 3, or critical values. And we only had one critical value, if you remember when we graphed out v of t. That was at the point 2.507. We did that back in part B. Feel free to check back there. Now, the only thing I'm going to add to what we did in part B is I'm going to rename this number value to a, and I'm going to store that on my calculator as well. So let me go to Desmos. Let me go ahead and take this value, and I'm going to copy that, and I'm going to paste that down here and call that a. Now I can use it whenever I need to. So we're going to have to test out the value of x at three places: 0, a, and 3. Now, x of 0 is going to be pretty easy because they told us that at time 0, the position of the particle is at time x equals 1. So x of 0 then is just 1. We kind of get that one for free. Next, we need to figure out x of a. For this, we're going to need our fundamental theorem. We're going to need to take our initial value of 1 and add to that the displacement between 0 and time a. So we're going to have 1 plus the integral from 0 to a of v of t dt. And let's go on Desmos for that. So we've got 1 plus integral from 0 to a v of t dt. And I'll just move this up a little so we can see it a little better. And that's about negative 2.265, which is bigger than 1. So far this is kind of the winner. But we also have to check out the other endpoint at 3. So for that, we're going to follow kind of the same process. Now we'll do x of 3 equals 1 plus integral from 0 to 3 of v of t dt. So 1 plus integral 0 to 3. And then going back to Desmos, this is actually super easy to plug in because I've already got the integral from 0 to a. So let me just make this the integral from 0 to 3. Just change that one little value, and that's going to be negative 1.197. Now the highest absolute value is going to be this 2.265. So that is the greatest distance, the max distance we are away from the origin with this particle.